Just about everything we know about our universe has come through the study of waves of light. In 1916, Albert Einstein predicted another wave, a gravitational wave, ripples in space-time. In 2015, these ripples were detected here on Earth for the very first time. They delivered a message to a very sensitive instrument called Advanced LIGO. And that message was of two black holes colliding 1.3 billion years ago. From that point on in 2015, a new window on the universe opened. And further mergers of binary black holes and neutron stars have been confirmed. Our guest speaker tonight is Professor of Cosmology and Gravitational Astrophysics at the University of Glasgow, as well as a senior member of the LIGO scientific collaboration of an international collective of more than 1,200 scientists, who, together with colleagues in the Virgo collaboration, reported the first direct detection of gravitational waves. For our speaker's outstanding work with the LIGO team, numerous awards have come his way, including Special Breakthrough Prize for Fundamental Physics in 2016, Physics World Breakthrough of the Year 2016 and 2017, and the President's Medal of the Royal Society of Edinburgh. In 2011, tonight's speaker was elected a Fellow of the Royal Society of Edinburgh in recognition of our speaker's contributions to research, teaching and public understanding of science, an area of outreach our speaker is passionately committed to. Among our guest speakers' outreach activities, he was Fellow of the Science and Technologies Facility Council, leading an international programme of outreach with schools and the public. A Fellow and former Chair of the Institute of Physics in Scotland and current Chair of the IOP Scotland Education Committee. In 2015, tonight's speaker was awarded an MBE in the Queen's New Year's Honours List for services to public engagement in science. So, here for you tonight, confirming that the real universe is more exciting than a galaxy far, far away. Please welcome Professor Martin Hendry, MBE.
Thank you for those very kind words of introduction. So it's a real pleasure to be able to join you. I'm sorry, of course, that I can't join in person, but nonetheless, it's an opportunity to meet some new faces, even if it's in the medium of Zoom. And that's always a pleasure. One of the things that I've enjoyed over many, many years is reaching out and meeting and working with astronomy societies across the UK. In fact, in 2009, International Year of Astronomy, we developed a project with the Scottish AstroSocs to build effectively a scale model of our solar system using the locations of the AstroSocs as the planets and working out how big the planets would be on that scale, all tied to Glasgow Science Centre close to our university as the sun. It's about 130 metres long, that building. So that was a chance to get out and about and to meet lots of the local communities that those astronomy societies engage with themselves. And I'm sure it's just the same for you. I was hearing a little bit about that, how you have your event coming up on November 13th, which is actually my birthday. So again, I have other plans that evening, but maybe sometime in the future, I will get the chance to come and join you in those sorts of open evenings where we get to do some stargazing ourselves. But what we're here to do tonight is a different sort of stargazing, I guess. A mixture of talking about the stars in the real universe, but a little bit about the stars of the silver screen as well. I entitled this The Science of Star Wars, and it's partly a little bit of a personal journey about, you know, how I got to be Professor of Gravitational Astrophysics and Cosmology when, if truth be told, what really started it all off was seeing Star Wars at an impressionable age. So what I seek to do is to weave in some real science as well to talk about gravitational waves, as we heard in that introduction. I'm a senior member of LIGO, part of that collaboration that made the first discovery and has continued to discover many more such sources since. So I can give you a little bit of a heads up about what is coming our way in terms of new LIGO results. But I want to set that in the context of the way that we've depicted the universe on the silver screen, specifically in the Star Wars films, although I'll mention other ideas that crop up in science fiction as well. And I suppose what it really does tell me is, just like we heard in the introduction, is that the real universe is, if anything, much stranger and weirder and more interesting and more surprising than anything dreamed up in George Lucas's universe. But that's not to say that I have a great deal of affection for Star Wars. I do. It's one of the things that got me interested in becoming a scientist in the first place. So hopefully, with a bit of a mixture of the real science and the science fiction, I'll give you some insights into some of the topics and some of the research that I have been involved in. So let's get that screen sharing going and we'll get things started. Right, so what I hope is going to work is that I will share this whole screen with you. Apparently you can see my screen. Oh, I did forget to check about the sound. You'd think after 18 months of lockdown I'd be actually quite good at this, but I want to make sure that I'm sharing sound as well as vision, and I believe I now should be. So let's make that big, and hopefully everyone can see my title slide. So can you just let me know if that's the case, just to make sure?
Yep, I can see that.
Yeah, excellent, excellent. What I've done, just because I'm at home this evening, I had hoped to go into the office, but various things happened, I wasn't able to. And I've got a second screen in there. It was at home in my kitchen for a long time, but I'm just gradually now moving back to my normal place of work, being the university again. So I'm just on my laptop screen. So consequently, I can't see you, but I can see the chat. So if you've got any questions, please do, ask as we go along. That's perfectly fine. Or indeed, I'll make sure that I'm done in good time so we can have a good chat at the end as well, if that would be helpful. So without further ado, let's press on with this personal journey through the Star Wars and indeed the real universe. So we heard a little bit about me already. Let me just flesh that out slightly. So cosmology is the study of the universe on its very largest scales. I'm sure I don't need to tell an audience of astronomers like yourselves about that, but I'm always at pains to emphasize that cosmology is concerned with the big picture. It's not so much interested in that particular star or this particular planet, but just the big picture of how the universe began, how big it is, why it's expanding, a truly remarkable thing that we've only known about for about 100 years. It's easy to forget that, and possibly what its fate might be in the future. And over my time as a cosmologist working in this field, well, as I like to put it to our students, we've reached a point where we probably know less about the universe now than we thought we did when I was a student myself. So the more things we learn, the more we seem to discover that it's rather puzzling. And I think that's partly one of the reasons why I find working in cosmology so interesting, because you just never know what's around the corner. So along the way, during my talk, we'll touch on such topics as dark matter and dark energy and say a little bit about that. But the other field that I've worked in for about 15 years now is the search for gravitational waves, which reached its big climax in 2015 with the very first detection. But I'm always at pains to emphasize that that wasn't the end of the story. It's really just the beginning. So what we're now doing is adding to the astronomer's armory a whole new way of looking at the universe beyond the visible light, which had served us well for the best part of 400 years. And indeed, the rest of the electromagnetic spectrum that we've been studying for not quite so long, but we've still learned a huge amount in the 20th century about the universe, with everything from X-rays to gamma rays to radio. Well, now we've got gravitational waves as well. So over the course of my talk, I'll weave in some aspects of that real science alongside the science fiction. But the science fiction is very much part of my story as well, because as I said, I was that impressionable youngster, just about 9 years old, I think, when the first film came out. And I had a very indulgent elder brother that took me to see it. And I was immediately hooked, immediately fascinated by what was going on the screen. So throughout my career as an astronomer, I've always tried to engage the public and to engage school students in the excitement and the mysteries of the real universe that I've been learning about in my research, But I've often gone about it by using science fiction as a way to reach them, as a way to hook in to the things that they are passionate about themselves, whether it's Doctor Who or Star Trek or the latest series on Netflix, or indeed Star Wars. Star Wars seems to be the one that throughout all my working life has never been far from the top of their list of favourite things. You know, from the age of 9 to 99, people relate to aspects of Star Wars, from Darth Vader to Yoda to Death Stars to lightsabers, all of that stuff. So as was mentioned, back about 10 years ago, I was a Science and Society or Public Engagement Fellow, and I called that project Exploring the Dark Side of the Universe, and specifically went about trying to explain the latest discoveries in cosmology and gravitational waves in the context of some of the language and ideas and images that we see in movies like Star Wars. So that's really how I'm going to approach my talk to you tonight as well for the next 40 minutes or so. So back in 2015, we weren't just getting ready to announce the discovery of the first gravitational wave event. We were also getting ready for Star Wars Episode 7, where after more or less about 20 years of there not being any new Star Wars films, and suddenly there was all of these new films to look forward to. So I was asked to write a short article by the journal The Conversation about what had inspired me to become an astrophysicist and the role that Star Wars played in that. So yeah, you know, fundamentally, it's all about recognizing that sci-fi doesn't get it right in terms of the science, but what it does is gives us a sense of wonder and amazement at just how incredible the universe is. And that largely was what got me hooked as that impressionable 9-year-old, and frankly, even as a pushing 50-year-old in 2015, had me very enthusiastic about Star Wars Episode 7 coming out then as well. And you might say that my research is all about studying what was happening in the universe a long time ago in a galaxy far, far away. So it's, a great privilege to be able to spend one's life working in a field which resonates so strongly with that world of science fiction that inspired me as a child. So these are all the reasons why talking about this is something I've always been passionate about. So what exactly are we going to talk about? Well, what I'd like to try and do is to cover 3 broad themes, to look at the science of Star Wars in the context of the space travel that we see in the movies, the weapons that appear, and I'm not going to glorify any of that, but there's some very interesting science to be dug into when you think about something like the Death Star that purports to be able to blow up an entire planet. Not that I'm recommending it's a good idea, but the science underpinning that is really quite interesting. And then we'll look at the planets and the star systems that are portrayed in the Star Wars universe and contrast that with what we've learned about planets and star systems in our own universe over an equivalent timescale. So over the 40 or so years, getting on for 50 years now, really, isn't it, since the first Star Wars films were shown in the cinema. How much more we now know about the planets and star systems in our universe than we did back then. So that's the game plan. And let's begin with a little bit about space travel. Let's see if I can get that to advance. Actually, before I just go any further, I'm just going to try and take the Zoom bar away. I do apologize for this. I should have done it earlier. I hope it's not been a distraction, but it's really not needed for this. So let me just remind myself how I do that. There we are. So that should give us a cleaner screen while I'm going through the talk. And apologies for not thinking of that sooner. Right, so I will try to sprinkle some quotes from Star Wars quite liberally through my talk. I'm kind of renowned in my department where the students recognize that I'm, a Yoda-like figure when it comes to quoting Star Wars, because anytime they try, they don't quite get it right, and I find myself having to correct them. So again, I do hope I get these ones correct, but I think this is certainly an accurate one from Star Wars Episode 4. This is where Han Solo says to the young and impressionable Luke Skywalker, as they're about to travel away from the planet of Tatooine, he says that traveling through hyperspace ain't like dusting crops, boy. Well, what exactly is traveling through hyperspace supposed to be? That's what we're going to focus on in this first of our 3 topics. So essentially, looking at hyperspace travel is resonating with so much science fiction. I'm also a big fan of Douglas Adams in The Hitchhiker's Guide to the Galaxy, and he captured that so well. He said that space is big. You just won't believe how vastly, hugely, mind-bogglingly big it is. I mean, you may think it's a long way down the road to the chemists, but that's just peanuts to space. And in some respects, that's a big problem when you're portraying the science of Star Wars on the big screen, because if you want to go anywhere, then to keep it scientifically accurate, the journey times, according to the physics that we understand today, would take an immensely long time. Now, there's a few get-out clauses because the rate at which time flows when you're traveling close to the speed of light is changed. And that means that as perceived by the astronauts on board the spacecraft, then not so much time would elapse for them. And that's an idea that's played with very nicely, I think, in the movie by Christopher Nolan, Interstellar, which I'm a big fan of as well. It's very different sort of sci-fi from Star Wars, of course, but the key science in Interstellar is absolutely spot on in many respects. And that's no surprise because the executive producer was Kip Thorne, one of my colleagues in the LIGO project and one of the 3 scientists awarded the Nobel Prize for that discovery. So somehow in his spare time, Kip Thorne managed to be exec producer for Christopher Nolan's Interstellar. And the science of Interstellar is, if you like, another version of this talk that I do that focuses a bit more on the specifics going on in that film. But if we stick to Star Wars for tonight, we've basically got this problem of the finite speed limit in our universe. Einstein's theories of relativity tell us that nothing material can travel at the speed of light and that nothing can travel faster than light. So that's a big problem if you're trying to get Han Solo from Tatooine to Alderaan within the 2 hours or so of a Hollywood movie. So what we see in Star Wars is a way to get round the vast scale of galaxies. Here's our own Milky Way galaxy, and it's 100,000 light years across, give or take. And that means even if you could travel at the speed of light, it would take 100,000 years to get from one side of the galaxy to the other. So what hyperspace is all about is giving us a convenient shortcut for sci-fi in the movies. Now, just like everything else these days, hyperspace has got its own Wikipedia page. And here's what it has to say. It says that hyperspace is a concept from science fiction relating to a superluminal method of travel. That just means faster than light. And it goes on to talk about it in terms of there being some sub-region of space coexisting with our own universe. Now, you know, this is not supposed to be Nobel Prize winning science. It's just a Wikipedia page probably put together more as a bit of a joke than anything else. But there's some useful insights we can take from this when we try and look at the idea of hyperspace in the context of what we know about space-time from Albert Einstein.
What's that flashing? Losing a deflector shield. Both traps themselves in. I'm going to make the jump to light speed.
So there's the first of my short clips. I hope you could hear the sound okay and it was coming through. That was from episode 4 as well. And that's where they actually make the jump to hyperspace. And we see all kinds of interesting artistic effects there. We see the stretching of the stars. We even see a kind of twisting of the stars. Now, I've not had time to update my talk on this yet, but actually I've got a paper which I've written with some colleagues that was featured in New Scientist this week. And it's about seeking to revisit some of the challenges we face in solving puzzles to do with dark matter and dark energy, but doing that in such a way that we include some twisting effects in space-time. So you could almost argue that George Lucas got there first in making it appear in that way when they jump into hyperspace. But what's all this space-time business really about? Well, that's where we can now begin to talk a little about gravitational waves. So we heard some remarks about that in the introduction, which covered it very nicely, really, and I don't want to go into too much detail here. But gravitational waves are a prediction of Albert Einstein's theory of relativity. They're all to do with the way that massive bodies in our universe can affect the curving of space and time. So our detection of gravitational waves from two colliding black holes was because their collision distorted the fabric of space-time itself and sent ripples spreading out through the universe that were detected by LIGO more than 1.3 billion years later. As I mentioned, this discovery was awarded the 2017 Nobel Prize. Here's our Kip Thorne that I mentioned before, the exec producer of Interstellar, along with his colleagues Rainer Weiss and Barry Barish. But it was, as they acknowledge themselves, very much a team effort. More than 2,000 scientists across the LIGO and Virgo collaborations involved in this discovery. I've mentioned that gravitational waves are like ripples in space and time. So what that's telling us is that we can manipulate the curving of space and time if you have massive bodies like black holes, or this is a little cartoon depicting what's probably more like a neutron star, a star that's so dense that all the neutrons are incredibly tightly packed together. Even just 1 cubic centimeter would weigh like thousands of tons. And when those two stars get close together and collide, it shakes up space-time a great deal. That's the gravitational waves, the ripples that we are seeking to detect. Now, the idea of hyperspace being fractured, being sort of distorted in a very violent manner does find its way into the Star Wars films as well. So we see not only that dramatic jump into hyperspace, where the Millennium Falcon is doing its thing back in the original Star Wars, but this is from a much more recent one of the films. This is from episode number 8, The Last Jedi. And what we'll see is what happens when a spacecraft goes into hyperspace and there's another spacecraft in the way. Not generally a good idea. So what we see is the release of a colossal amount of energy as that spacecraft, the Radius, I believe it's called. I'm not quite as expert in the names of all the craft as I used to be as a youngster, but I think I've got that one right. The Radius is heading off into hyperspace in the same direction as the flagship of the Imperial fleet. So this is how they thwart the baddies on that particular occasion, because it ruptures the spacecraft and indeed many of the other spacecraft around it. So, you know, what that seems to be hinting at is that there's a vast amount of energy locked up in space-time. And that's very much what we are seeing when we witness the collision of two black holes. So this is the cartoon, you know, and maybe owes a little bit to Hollywood itself, that we used in the press conference to announce our very first detection of gravitational waves. It shows those two black holes in a kind of schematic showing how space-time is distorted as they orbit around each other. Many of you might have seen this before. And then as the black holes merge, you get this burst of gravitational waves emitted. So think of that, if it's not too fanciful, a bit like the director suggesting this burst of energy as the Radius makes its jump into hyperspace. Well, that's all very well. But what about this chap? Where does Darth Vader fit into it all? Well, of course, it was different baddies by the time it came to episode 7, but I grew up with him as the ultimate nemesis. And I think it was him that said, never underestimate the power of the dark side. And the thing is, our calculations of the energy that was released during the merger of those two black holes very much back up what Darth Vader had to say. Because in about 1/3 of a second, the equivalent of 3 times the mass of the sun was released in gravitational wave energy. as space-time reorganized itself following the merger of those two black holes. So if we work out what that is as a power, because power is energy divided by time, so you've got 3 times the mass of the sun, convert that to energy, you multiply by c squared, that's the famous E equals mc squared, c is the speed of light, and then you divide that by 0.3 of a second, you've got yourself a power in watts, and it happens to be about 50 times greater than the combined light power of every star in every galaxy in the entire universe. Now, it didn't last for long, but that gives us some insight into how much energy is locked up in the fabric of space-time itself. So the whole idea of hyperspace is about tapping in to that energy. So, of course, I've no idea if this will ever be possible, but there are some honest to goodness scientific theories out there which play around with this idea of the energy trapped in space-time. And in fact, I've worked on them myself. So they involve, for example, universes in which there are extra dimensions, not just the 3 dimensions of space and 1 of time that we perceive, but other dimensions which are wrapped up on themselves so that we only see the 3 spatial dimensions. But it might be the case that gravity can propagate through those extra dimensions, while the other fundamental interactions like light and magnetism and electricity are confined to the dimensions that we perceive, the 3 space and 1 of time. So what this offers is an interesting way in which we might test if any of those ideas have any truth to them. What we would like to do is to observe an event in the universe, a collision, an explosion, where we observe it in both gravitational waves and in light. And if the gravitational waves arrive at a different time from the light, then that would give us some insight into those extra dimensions. Do they exist? How large are they? Because that would affect the propagation of the gravitational waves, but not the propagation of the light. Now, fortunately, in 2017, we got just such an opportunity, and that was the second of the Physics World Breakthrough Prizes that you very kindly mentioned at the beginning. This was the observation of 2 colliding neutron stars, much closer to home than the black holes that we usually see, only about 130 million light years away, not billions of light years. And on this occasion, as I'm sure many of you will remember, we actually did see the accompanying electromagnetic radiation. First, we saw a gamma ray burst, which is what this artistic painting is trying to capture, done by one of my LIGO colleagues in the US. And then we also saw optical light from the aftermath of that collision, which is what we call a kilonova, like a miniature version of a supernova. But what we believe sparked all that off was the collision of the 2 neutron stars that we saw in gravitational waves. And the interesting thing is, well, let me just first play the sound. So what you heard there, I hope you could hear that okay, was the gravitational wave pattern, what we often refer to as a chirp, represented as a sound wave. They're not sound waves, but it's a convenient way to experience them. You can draw the graph, but you can also hear the sound, because the frequency of the gravitational waves that LIGO can detect corresponds to frequencies that the human ear can hear. So we heard the chirp of the binary neutron star merger, and only about 2 seconds later, there was the ping corresponding to the arrival of gamma rays from the aftermath of that, the gamma ray burst. Now, the fact that they arrived 2 seconds later is, we believe, because they were emitted 2 seconds later. It takes a little bit of time for the effect of the gravitational wave emission to trigger the gamma ray burst. But think about it, only 2 seconds delay over 130 million years. So even if they were emitted at exactly the same time, what that allows us to do is to constrain very, very precisely the difference in speed between gravitational waves and light. Now, if there are no extra dimensions, according to Einstein's theories, gravity and light should propagate at the same speed, the speed of light, or you might equally say the speed of gravity. If there are those extra dimensions, then they'll get out of step with each other. And for want of, just to let you see the maths, again, I know it's not everyone's cup of tea, but what we were able to do was to put very, very strong constraints on the difference in speed, this delta V, between the speed of gravity and the speed of light. So far, we don't seem to see any evidence of those extra dimensions that we might imagine as harboring hyperspace in some complex way. But we continue to work on this topic. And in fact, I just had a paper with some colleagues a few weeks ago, which was looking firstly at a reanalysis of that binary neutron star collision, just improving some aspects of our analysis, but also looking forward to a space mission that's coming up in the 2030s that will look for gravitational waves from much more massive black holes. The mission's called LISA, and actually LISA will be better at doing this test of does light and gravity travel at the same speed. So we might have to wait another decade or so, but eventually, if there are those extra dimensions out there, then we think that we'll be able to say something about them with the kinds of data we'll have in the 2030s. So what could those extra dimensions mean for something like hyperspace? Well, again, really there's just cartoons here. There's no proper science as such. But the basic idea is to think about the fabric of space-time, not just on the large scale, but on the microscopic scale, on the scale of the quantum realm, to bring in terminology from another part of sci-fi. I suppose that's a phrase we hear in the Marvel universe with all the stuff from Endgame about traveling through time by exploiting the quantum realm. Well, in the same way, ideas about hyperspace might have something to do with taking a shortcut through those extra dimensions, which is a bit like what this cartoon is trying to represent. And perhaps the way you do that is by taking a shortcut through something like a quantum tunnel or an Einstein-Rosen bridge. There's a lot of scientific language to support this, and sci-fi has occasionally tried to tap into that to make all of this sound a little bit more plausible. Well, is it really plausible? We're not sure. But if it's good enough for Kip Thorne, it's good enough for me. And Kip Thorne, back in the 1980s, was science advisor for another film and another book. The film was actually made in the 90s. Again, I'm sure you're aware, this is Contact by Carl Sagan. So Kip Thorne came up with this idea of traveling through wormholes as a way to take a shortcut through extra dimensions. So I guess all I'm really trying to say is that it still is an active area of research. And it's perhaps not as completely off the charts crazy as you might at first think. But there's a lot of technical issues with it. How do you make a wormhole big enough to fit a spacecraft through, for example? That's far from easy, given that typically wormholes will exist on the quantum scale that's unimaginably small, smaller than even subatomic particles. And we don't have those wonderful pin particles that you have in the Avengers to shrink you down to that quantum realm scale. So as I said, these ideas have been explored a lot in Interstellar as well. And from a more hard science fiction perspective, proper rules of physics, not quite as plain fast and loose with them as they do in Star Wars, but all good fun. And frankly, it's also likely to have something to do with what's going on in Back to the Future. Because if we could harness gravity in the way you see in Interstellar, and frankly, the way you seem to see in Star Wars as well, then that would open the way to anti-gravity machines. You would have your hoverboard like Marty McFly has in Back to the Future 2. I'm still waiting on mine, and that was supposed to be happening in 2015. So we're a bit behind the curve on that one. But the plain truth is that gravity is still pretty mysterious in some respects. We can measure the gravitational field of massive bodies, but we can't just switch it on and switch it off. We can't create a device that generates its own gravitational field other than just making it very massive. And carrying a black hole around in your pocket isn't a very practical method for curving space-time. But on a fundamental scale, it does seem as if the fabric of space-time can be affected by some pretty strange phenomena, not least what we have come to refer to as dark energy. It really does sound like something out of Star Wars. And that seems to almost function like anti-gravity. It seems to be stretching the expansion of the universe, causing it to speed up. So if we ever get to properly understand what dark energy is, who knows, maybe it will give us some insight in how to control gravity on more terrestrial scales. That's certainly how it seems to work in the Star Wars universe, because it's not just about jumping into hyperspace, but also much more mundane situations in which anti-gravity is just part of the landscape. So, you know, this is Craig Lars, Owen Lars's uncle, and he is sitting on, I guess, well, you can't call it a wheelchair because there's no wheels. It just floats there and can float along without any forces being pressed down on the ground, the way that our normal understanding of physics would require. And the same goes for Jar Jar Binks in his floating platform in Star Wars Episode 1, or for that matter, Obi-Wan Kenobi when he's being held captive by Count Dooku in Episode 2. Everywhere you turn, it seems as if gravity can just be switched on and switched off in a manner that we just cannot do in our universe. And that brings us to topic number 2, in the Death Star. But just before we talk about the weapon aspect of the Death Star, let's just say a bit about the whole controlling gravity. So let me note that the Death Star was first seen in Star Wars in 1977. And that was 4 years before the Voyager spacecraft visited Saturn. So nowadays there's even workshop manuals you can get for the Death Star. But when it all began back in the Star Wars premiere in 77, as I said, was several years before NASA astronauts got this image of the moon Mimas in the Saturn system in the early 1980s. So they're spookily similar. I'm not quite sure what that means, but their differences are really important too. As you learn from looking at that owner's manual, inside the Death Star, there's all manner of equipment and habitation levels and, you know, places for all those stormtroopers to run around. Inside Mimas is just a big dirty snowball. So the gravity of Mimas is very weak. And moreover, the gravity on the surface is different from the gravity inside. That's not how it works in the Death Star. So that's another indication that somehow in the Star Wars universe, they can control the force of gravity. But of course, they can also use the Death Star to wipe out planets. Not that we're recommending that, but let's have a think about the physics of that and whether it makes any sense whatsoever. So the Death Star is really big. It's huge. Again, you can see it dwarfing the Star Destroyers here. This is from Rogue One, not one of the main Star Wars films, but I liked it very much. I thought it captured the spirit of Star Wars very well. And another little phrase for us here from Star Wars Episode 4, where Darth Vader says, "Don't be too proud of this technological terror you've constructed." Well, it is pretty terrifying because this is the kind of thing that they can do to planets. Here is the destruction of Alderaan.
Commence primary ignition.
So what can we say about the science depicted there? Well, okay, there's the sound in space. Let's not go there. That's a problem. There's also the fact that the laser beams seem to change direction. Well, laser beams don't do that. We'll come back to that in a moment. But let's just think about the energies involved. Let's just focus on that first. So the power capable of destroying Alderaan in 0.25 of a second, well, crikey, we're almost getting on to the level of power that we talked about for the gravitational wave event. It's that many megawatts. I won't even try and quote the number, but it's an awful lot of zeros. And that equals to the power output from the sun in about a month. So the Death Star must have mighty impressive batteries to store up all that power and release it in such a short time. And actually, this question around the power and where that energy might come from and how much energy you need to destroy a planet in the first place. Well, this was a little paper written by two students from the University of Leicester. So it's clearly not just me that is thinking about these kind of things through the perspective of proper astronomy. And I frequently chat to our own students in Glasgow about these questions, just to get them thinking about how what they're learning in the lectures might relate to what they see in the films. So ultimately, what it boils down to is that to destroy a planet, you've got to put into the planet all the energy that is in the form that we call potential energy, the potential energy that's binding the planet together due to its gravity. And that's a heck of a lot. That's where we arrive at this number corresponding to the output of the sun for several months. And it's interesting to see as the Star Wars films evolved over the years. Firstly, there's a little bit of Death Star envy here because the Death Star just kept getting bigger. Well, okay, this one wasn't called the Death Star, but that's from episode 7. And what you see there is really going the whole way. It's not just building a space station, but embedding Death Star-like technology into a planet itself. So that was the Star Killer base that we saw in episode 7. And there was a real sense where what was going on there was capturing somehow the energy of a star, storing it in the Star Killer base, and then unleashing it to wipe out the planets. So again, the science is, fairly ridiculous, but there's some interesting links to what we actually have worked out about the amount of energy you would literally need. It would correspond to several months' power output of a star like the sun, and that seems to be what the Star Killer base was up to when it gobbled up all that energy from a star and then unleashed it to destroy the planets. Let me just say a few brief words about lightsabers. An elegant weapon from a more civilized age, as Ben Kenobi said. And here we see Qui-Gon Jinn from episode 1 brandishing his lightsaber. All I really want to highlight is ideas about what the lightsaber might be. And I'm afraid even the films aren't terribly consistent about this, because on the one hand, you sometimes hear them being referred to as laser swords, and sometimes not referred to as plasma beams, but the implication is that they behave like a plasma beam. So what exactly do we mean by that? Well, a plasma beam is really just like a bolt of lightning. It's an electrical discharge that heats up a gas so much that it turns it into plasma, that the atoms in the gas get torn apart, the electrons and the protons, so that it becomes electrically charged. And it can store a heck of a lot of energy. It can do a lot of damage. So could lightsabers be plasma beams? Well, the laser sword argument is said by a few people. Anakin Skywalker, no less, in episode 1, and then Snoke, Supreme Leader Snoke, I think it's in episode 8, refers to them as laser swords. But there are kind of some problems with them being laser swords. I know they look super cool. I did a poll of my first year undergraduate student class, which was the best lightsaber battle, and they all went for this one. So I thought I would share that with you. Again, it looks great, but lasers just don't behave like that. Lasers don't stop. Well, they do if they bounce off a mirror, but there doesn't seem to be a mirror at the end of the beam. So if they are, in some sense, a laser, then it's not like any laser we have in Earth. Lasers are basically light. And that means that when two laser beams interact, you wouldn't get that funny noise. You wouldn't get them pushing against each other, at least not with the kind of powerful lasers that we've been able to build so far. But could they be plasma beams, or, to use the language from the films themselves, ion beams? Because remember, that's what a plasma does. It makes ions because the protons and electrons get torn apart in atoms. So here's a little clip from The Empire Strikes Back, where Princess Leia is referring to an ion cannon.
Stand by, ion control. Fire.
So they seem to pack quite a mighty punch as well. And those, I'm not saying we're going to develop them anytime soon, nor should we aspire to do so. But the physics behind a weapon like that is actually not so crazy. And I'm old enough to remember when Ronald Reagan developed his so-called Strategic Defence Initiative, or Star Wars program, and this was one of the types of weapons that they were looking to unleash. Okay, not quite as effective as you see in the Star Wars films, but a pulsed energy beam that would disable an incoming missile. You know, them were the days, crikey. Of course, they never worked, but to think that that was what we were trying to do, and maybe it's connected with the fact that Reagan was an actor himself and was inspired by what you see in the Star Wars films. Anyway, pressing on, the idea of plasma does have very firm roots in our real universe, and this is at the heart of what we're trying to do by creating controlled nuclear fusion. That means to create a plasma, just like you have in the heart of the sun, consisting of hydrogen or other light elements, and then fusing that into heavier elements and releasing a lot of energy in the process. But one of the key aspects of a plasma is that you are separating those positive and negative charges. So if the lightsaber beams really are plasmas, it kind of suggests, because they would conduct an electric current and because they would be affected by a magnetic field, that maybe this would be an effective deterrent against an oncoming Jedi Knight with a lightsaber. Who can say? But again, it's just interesting to think about some of the physics that might be going on there. Let me now move to my final topic, and I'll be quite brief on this. I don't want to take up too much time, but I hope you're enjoying it so far. We're going to say just a little bit about the planets that you see in the Star Wars universe and how those might relate to what we've learned about our own universe. Now, here's a quote from episode 4. Luke Skywalker says, "If there's a bright center to the universe, I'm on the planet that it's farthest from." This is Tatooine. He had a bit of the wanderlust. He didn't want to stay in Tatooine. He wanted to get out of there double quick. And it's a real sign of what a backwater Tatooine must have been that he had a similar disdain for Jakku, which was the planet that Rey grew up on from Star Wars Episode 7 and 8. And here's what Luke has to say about it in The Last Jedi, Episode 8.
Where are you from?
Nowhere.
No one's from nowhere.
Jakku.
All right, that is pretty much nowhere.
Yeah, I hope you could hear that. It was a bit quieter, but great disdain for both Jakku and Tatooine. So how typical are those of the Star Wars universe? Well, here's a little game I sometimes play with the undergraduates. Don't worry, I'm not going to test you in this. But one of the lecture courses I teach, because it's all been online in the last year, what I've done is I've used a different Star Wars background for every one of the lectures. So my first question to them in the morning is, which planet am I on? Which is maybe a question they're asking themselves quite a lot in my lecture courses. But it's a remarkable variety, and it's also remarkable how many of the students can name them right away. So there's a huge variety to choose from. But how exactly does all of that compare with what we are beginning to learn about our own universe? Well, here's the galaxy at the end of Star Wars Episode 5. This is my favorite, The Empire Strikes Back. And I remember even as a youngster thinking, wow, that looks great. So let's watch that little clip. So there's the Millennium Falcon heading off into that spiral galaxy, presumably the Star Wars galaxy. And well, if we look at a map of that features in, if I get this one right, I think this one is Episode 7, you can see, of course, lots of individual stars and the odd planet named, if you could zoom in and read the text. The truth is, our own galaxy is on a vastly huger scale than what we seem to see portrayed in the Star Wars galaxy. As we mentioned earlier, our galaxy is 100,000 light years across. At best guess, it's got somewhere between 1,000 million stars. Sorry, let me try that again. 100 billion stars is what I meant to say, and 400 billion stars, a vast number. And therefore, you know, it's perhaps not surprising that what we're beginning to learn about our own galaxy is putting into the shade what you see in the Star Wars universe. So for example, I remember as a youngster thinking Tatooine was pretty cool. Well, okay, it's actually very hot, but cool in the sense that it was a planet going around a binary star system. And in fact, what we've discovered is that there is such a planet out there in our universe, in our galaxy, and we'll come to that in a moment. There's also, from the more recent movies, systems where there are multiple planets orbiting very close to their parent star. And yet, lo and behold, we've discovered that kind of thing as well in recent years in our Milky Way. So let me just say a little bit about how we find those planets. Again, this might be quite well known to many of you, but just to emphasize where all of that is heading in the next few years as I wrap up my talk. So there's an excellent website you can check out that gives a rundown of how many exoplanets, extrasolar planets we found. And forgive me, I meant to update this slide. I'm sure it's a much bigger number now. This is from a few months ago, but there's thousands of them out there. And we're going to find more. If we look at upcoming telescope projects, one that I'm excited about for the next few years is the Extremely Large Telescope. So here's an artist's impression of that on its mountain in Chile. And that has such a high resolving power and light gathering power that it will be capable of directly imaging planets around nearby stars. So if there was a planet like Jupiter orbiting a star about 30 light years away, then the Extremely Large Telescope should be able to directly image that. But in fact, most of the ways that we found those thousands of planets have been indirect. So the ways we do it are using Doppler wobble and the transit method. So the Doppler wobble is all about Newton's gravity. It's about the effect that an unseen planet can have on its parent star. It will cause the planet to wobble in much the same way as two people on either end of a seesaw will wobble up and down. And if you have one much more massive person, like when I used to take my daughter when she was much younger, and I'm close to the middle, then I would hardly move at all while she would happily move up and down. And that's a bit like what we get when you don't see the planet, but you can see the star wobble because of the gravitational pull of the unseen planet. And often that's too hard to measure directly. You don't actually see the star move, but what we can do is we can detect the movement through the shifting of lines in the star spectrum. So what we're actually seeing is motion of the star away and towards us, back and forth along the line of sight, due to the tugging of the unseen planet. So that method is one of the two that's proved hugely effective. The other one is called the transit method, and this is where the planet causes the light from the parent star to be temporarily dimmed as the planet crosses in front. So if you make a curve of the brightness of the star, then you get that dip as the planet crosses in front. And in fact, just today on the web, I saw on the BBC News page a very interesting story. I wasn't aware of this study being carried out, but this is looking for transits in X-ray data. And it seems to have found some evidence of the existence of a planet orbiting in an X-ray binary system, not in our galaxy, but in M51, a spiral galaxy that's in our close neighborhood, but the first evidence of a planet outside our galaxy. So that was pretty exciting too. And probably the champion of the transit method has been the Kepler satellite, which was launched in 2009 and operated for about a decade and clocked up thousands of planetary discoveries. And one that it discovered was the one I mentioned before. This is our analog of Tatooine, Kepler 16. So it's a planet, this is just an artist's impression, of course, but it's a planet orbiting a binary star system. And perhaps, not too dissimilar from what's being depicted in Tatooine, where you see the twin stars in the sky, just like I had in my backdrop. And then also what Kepler has thrown up is the TRAPPIST system, where there were multiple planets that are so close to the parent star that they would be inside the orbit of Mercury if it was our solar system. And that seems to mimic that Hosnian prime system that we saw earlier from Star Wars Episode 7. So everywhere you turn, our real galaxy, our real universe seems to throw up surprises in the types of planetary systems, which are, if anything, even more remarkable than what you see in the Star Wars films. So where's all this going to take us? Well, let me just end on a few remarks about an exciting upcoming development. So here's an observation with the Hubble Space Telescope of a planetary transit. And what you see is that there's not just a sharp drop, but there's a curve. And that curvature is telling us something important about the planet's atmosphere. It's giving us information about the gases in the planet's atmosphere. So here's a kind of cartoon of that. What we see is that if you look in different colors of light, then you see the dip have a different amount. So more light is absorbed at some colors compared with others. And that, as I said, gives us insight into the gases which are present in the planet's atmosphere. So the basic idea is that as the planet transits in front of the star, then we can measure its size from the width of the dip, but we can also get insight into the atmosphere from the shape of the dip as well. Now, all of that is exciting enough in terms of what we can currently do with the Hubble telescope and other ground-based telescopes, but it's going to get a whole lot more exciting in the next few years, because Hubble has already done this kind of analysis looking at spectral lines and indicated the presence of water vapor on planets in the habitable zone of other stars. That means the zone in which liquid water could exist. So we don't just know that it could theoretically exist, we see evidence of it existing in the planet's atmosphere because of the spectral features that Hubble was able to observe. And that's the kind of thing that the James Webb Space Telescope is going to do as well, and much better. So it's scheduled for launch on the 18th of December, 2021. And in fact, one of the potential problems with the launch date has been overcome, because that launch window is now there for the James Webb to use. There was a mission launched just a couple of days ago called Lucy, which was going to visit a number of asteroids, and that launched successfully. So that's freed up now this window in December for James Webb. So fingers crossed it all goes to plan, because a matter of a few years, the James Webb Telescope will be analysing infrared light from stars dimmed by planets passing in front of them. And that will tell us the physical properties of those planets, including their temperature, their mass, and the chemical composition of the atmosphere. So we still might be a long way away from finding life like Yoda, but we can see a path towards doing that if we can characterize the atmospheres of planets going around other stars. Then if there is life out there, who knows, we might see the signatures of it before too much longer. I certainly hope so. And I hope you've enjoyed this little personal journey through my career as an astronomer, and also my career as a huge Star Wars fan. So may the Fourth be with you. Thank you very much again for the invitation.
Thank you, Martin. Excellent lecture. Thank you very much.
Yes, thank you very much, Martin. Very interesting, that.
Yeah.
One of my favourite sci-fi films, that.
Star Wars.
Yeah.
Well, I thought in the end that just doing a straight talk about the gravitational wave discoveries would have probably been very interesting to you all too, but this was a way to weave a little bit of that in as part of the bigger story.
Yes.
And sometimes it really does get quite hard to tell the science from the science fiction. So happy to answer questions if people have any. And again, do forgive me if I've taken more time than you'd expected. I kind of lost track of time a little there, but I see you're just coming up on 9. So again, at your disposal if you've got any questions.